Might as well dive right in. Pause. Share screen. Let's go to my application. Okay. My beloved MS Paint canvas, of course. And once again, I keep on forgetting to say this, but follow us on social media. It's really good to have updates, and I don't know, Fiveable is just pretty cool. They have good memes, and yeah, just go and follow them. It's pretty fun. Okay, so let's start with this question. So today I'm going to cover force diagrams, and if you know anything about physics, we love force diagrams like so much. And these are probably very simple, right? This is just like pretty much in 1/2 dimensions, and they're all connected by like strings, so you can pretty much consider it one dimension. But yeah, let's start by going over this force diagram. Let's use this nice blue here. So let's go over all the forces that we usually see in this world. So right now, I'm going to try to calculate the total acceleration of this system. So like probably the acceleration of one block, because the acceleration of one block is going to be the acceleration of all of the blocks. And I also want to solve for tension. I didn't write that here, but I would like to solve for tension by the end. So let's talk about forces, right? So what forces are out there? You guys want to say anything? You guys, any idea what forces are? Force is equal to mass times acceleration. It's the second law, of course. So what type of forces are there? So let me start. There's a gravitational. Yes, gravitational. At least in this system. What else is there? We usually denote this with a T. And it's very specific for these types of questions. Yes, tension. Okay, let's go a little bit farther down. This one, today we're not going to talk about it, but sometimes we denote friction or frictionless surfaces with like a dashed line. So there's another force that we're not going to consider today, which is friction. So forces can cause change, right? So let's say you're looking at like this system in particular, right? The only force that is acting in the vertical direction is this block, right? But then we can ask what forces are happening on this block here. There's just the gravity force that is going down, the normal force that's going up, right? There's no force going this way, or any force. Well, you can talk about the tension, but yeah, pretty much if it's staying still on this block, there's not going to be any horizontal force because there's no frictional force. So the way that these two blocks interact, because you would expect if you had a larger mass here, this would slow down, right? And you have to wonder, like, what's the relationship between these two masses' accelerations? And that relationship is completely derived through tension. So that's also why we want to solve for tension in these types of equations. So let's get started with this guy over here. Let me try to minimize this portion. Okay. See if I can just like make it smaller. Small. Okay. So for this graph, let's label the forces. Mass times gravity. Ooh, I'm still using the I sometimes I realize that like it's not about having a big brain, it's about having a small brain and knowing how to use it. Like I'm pretty stupid, but sometimes you gotta finesse. So this is mass times gravity, right? And this particular mass is 3 kilograms. And the gravity is 9.8. 9.8 meters per second squared. And this one, you also have a downwards force. You have 5 kilograms times 9.8 meters per second squared. Yes, indeed. And I'll go into an explanation of that. So just like an interesting fact about tensions, the tension's going to be completely uniform throughout the entire string. Like you're not gonna like cut through the middle and suddenly this tension's like really strong and this tension's really small. The entire string has to be completely uniform. And this is also like a general fact about a lot of different like simplified bodies. Like if we start talking about bars, right? Because this isn't like in AP Physics 1, right? But when we have a bar, like we assume that the entire thing experiences the same force. So it's like a simplification of the system. So like if we put like a mass here, this entire bar experiences the same amount of force throughout the entire thing. This is the same with tension in strings. You just pull the other way, right? Okay, let me delete this guy over here. Okay, so once again we have tension going this way, and tension going this way. So I guess like a way I like to think of this particular problem. This is actually really simple. You can even imagine this as 2 blocks on a string, just vertically, not vertically, just horizontally on a flat surface. This is 5 kilograms, and this is 3 kilograms, and they're both just accelerating at 9.8 meters per second, right? This is an equivalent system that will result in pretty much the same tension and the same amount of like acceleration as the entire thing. But let's just go over how to like solve this like the really simple way. Okay. So you want like total force in y, right? Because these objects are like going in up and down, right? So we want to find the total force, right? So this one, let me just do a simplification. So we kind of, just by intuition, we can tell that this guy's going to go down, right? And this guy's going to go up, right? This one's a heavier box. So this is going to be 5 times 9.8. And then this is going to go up, right? So this is going to be minus 3 times 9.8, right? Does that make sense? Or do I need like a further explanation of that? Or like technically, if you, let's just define acceleration downwards as positive. Or perhaps you should define it negative. It still works out if it's negative. But yeah, so the acceleration downwards here is going to be 5 times 9.8. And then the force down here is going to be 3 times 9.8. So the way you can once again imagine it is that there's a force. Let's just go back to our 2 blocks on a string metaphor. So what you can imagine is that there is a force going this way that is 5 times 9.8, and a force going this way that is 3 times 9.8. So if they're going in different directions, of course you have to subtract the 2 from each other to get the resulting like total force that's acting on the system, if that makes any sense. So we're just gonna multiply those 2 together. Let's just do a simplification of the acceleration of gravity. Right? Let's just say this 50 minus 30 is equal to 20 newtons, right? So this is a total force that's going to act on this guy downwards. So this is the force that's pulling it down, along minus the force that is pulling the other way, which is pulling the other block down as well. So it's like a balancing of these 2 forces. So there's a total of 20 newtons acting on the entire system. And if we know that force is equal to mass times acceleration, we can find the total amount of mass, which is 5 kilograms plus 3 kilograms times acceleration is equal to 20 newtons. And this is going to just be 20 divided by 8, which is equal to, quick maths, 5 halves, 2.5? Yeah, 2.5 meters per second squared. Okay, and like the simple way of thinking of this is that you just take the ratio of the masses. Okay, this is a special case for just pulleys because we're talking about like a very linear force. But you have 5, let's draw it over here, 5 kilograms going down, 3 kilograms going up, right? And you got like a pulley system going on, right? What you could do as a shortcut for these problems is just find, like this is 3/8. Okay, let me try to reword this. Let me make sure I'm doing this right. 3 divided 8. Yeah, that's 30 cents. Okay, let's do a shortcut for like a more simple. So let's say that you have 2 masses, right? They weigh the exact same amount, so let's say they're both 2 kilograms, right? That implies that the acceleration is going to be half, right? Because no, that implies that they're going to be in the same position, right? So this is in the same place, this is the same place, the forces counteract in perfect equilibrium. But once you have like this double, right, we can do the entire thing over again where we have like 2 times 9.8 minus 4 times 9.8. You might notice something like very peculiar. It's just like 2 minus 4, which is just 2 times 9.8, right? So you just subtract the masses between the two. It's equal to 20 newtons, right? And you just do 20 divided by the addition of the 2, 20 divided by 6. That's going to be 3 1/3, right? And from, let's see. Yeah, so pretty much what you can do is just find the difference of these two guys. They're pretty much the same. I can go over it really quick after this, but yeah, if you want to take a shortcut on these Pulley questions, you just take the difference between these two guys. So mass 2 minus mass 1, and divide that by mass 2 plus mass 1. And then I think you multiply that by 9.8. I think this is a shortcut I just made up in my head. Let me make sure that this is right. 5 minus 3 is 2 times 10. Yeah, and then yeah, this is basically the shortcut for any sort of Pulley question right here. Okay, so let's go over. Let me scroll all the way down here. Let's go over gravitational force and wait, totally unrelated. But what's the difference between magnetic and electric force? This is E and M. I took E and M last semester. I'll be completely honest. For the most part, I forgot. But let's see what I remember. Magnetic field. There's 2 different sets of equations for magnetic field and electrical force. But what was that? Yeah, I'm not gonna try to say something that I don't completely understand, but I know that there's like a different set of rules for each one. But you can derive the relationship between the two is that like when you have a current running through a wire, it creates a magnetic force surrounding it. So there's an equation for that, which I forgot. You can look it up. But pretty much the two you treat differently. But yeah, that's pretty much the only relationship you can find between the two. And what is it? I can give you like a more conceptual explanation on why that is, but there is an equation to relate current inside wires and magnetic force and electrical force. Okay, I think electrical force refers to Coulomb's law, right? I should just K Q1 Q2 over R squared, and this is really similar to gravitational force. Right now we're talking about gravitational force, so this is somewhat related. So just like, even though this is not completely related to you, Stella, but like if you think about how Coulombic action works, you got like two, well, it depends whether or not they're positive or negative, but you have, let's say we have like two particles, right, with opposite charges. I mean, it's not surprising that like the relationship between like these two guys are R squared, right? If you think about like the surface area, right? So 4 pi R squared. This is a derivation I'm making up in my head right now. But yeah, if you get closer, that like interacting surface area also increases proportionally. So that's why there's an R squared relationship in there. And it's the exact same thing with gravitational force. You got just two bodies with like iso force lines. I forgot what they're called, but you can see why they're somewhat related. But anyway, going back here. Ooh. Yeah, pretty much. If you want to do these types of equations, this is the go-to. Okay, let's see if I can make up another relationship for this guy right here. So once again, oh, I forgot to calculate the tension. Yeah, let's calculate the tension. We calculated the acceleration to be 2.5 meters per second squared, right? So the tension is going to be the force that is counteracting the motion to prevent it from going at its initial acceleration, right? So you can think of this conceptually as 5 times 9.8 meters per second, right? So that is a force going downwards. But we need a force going counteracting, going upwards, minus another force. Right, let's do plus another force is equal to 2.5 meters per second squared. But this is multiplied by 5 kilograms. So there is a force that is preventing this system from going the full acceleration, but in fact it's going at this acceleration instead. So what you can do is just subtract the two. I'll just do the simplification of 10 over here. And just say, so, well, my work is really messy. 10 minus 2.5 is equal to 7.5. So you do such a 7.5. Okay, this is just basic algebra, but you just pull this guy over here, and it's going to be 7.5 times 5. Right, and that's just going to be the force of tension. Yeah. Hope that's right. Okay. Let's take this guy over here. Okay. So once again, let's draw our free body diagram. There is no frictional force, so we don't need to consider any force that's counteracting going this way. So that's going to be 0. Force is equal to 0 this direction. But we have in mass times gravity, 3 times 9.8 meters per second squared. Today we're using simplification. So let's just say the force is equal to 3 kilograms times 10 meters per second squared, which is equal to 30 newtons. Yeah. You have this one as mass times gravity, but you also have it completely counteracted by this one. So there's a total of 0 vertical force. It's not like we could have done anything with that vertical force, but yeah, pretty much we just disregard that. And the only force that is acting on here is tension, which is pointing inward. Yes. Okay. So the total force that is pulling this entire thing down is the force of gravity acting down here, right? That's going to be 30 newtons. Is equal to mass. So we want the total mass because we want to find the total amount of acceleration. So this is the net force equation, right? So there's a total of 30 newtons pulling like along this line, causing this tension. So 30 newtons is equal to total mass, which is 5 kilograms due to 3 plus 2 3 kilograms plus 2 kilograms is equal to 5 kilograms. And you want to find the acceleration, right? So acceleration is going to be 6 meters per second squared. So that's just 30 divided by 5. I remember my teacher teaching me a shortcut to this. Let me see if I can figure it out. Let's see. I can't figure out the shortcut right now. But, yeah, I'll get to the shortcut if I ever figure it out, but not right now. Anyway, acceleration is going to be 6 meters per second squared. Okay. Let's see. Now I'm kind of curious if there is a shortcut. So 3 kilograms and 9.8 divided by 3 plus 2. No, there's no shortcut to that. You just got to do it like straight by hand. It's pretty simple anyway. And then what you can do with that force or with that acceleration, now know that the current acceleration is 6 times 6 meters per second squared times 3 kilograms. So this is just the force of the block, force of 3 kilogram block, right? So right now it's accelerating at 6 meters per second squared. And then we want it to, so that's going to be equal to the total force that it would have had without the tension. So with 0 tension, it'll be 3 times 10 meters per second. I should put units on that. Kilograms, meters per second squared. Plus tension force. Or you can just subtract. I don't know. Sign conventions at this level, I don't think really matters as long as you're aware of what makes sense, like intuitively. So let's just do 3 kilograms times. Oh no, we're talking about tension force. We're not even talking about that. Okay. Minus tension force. Okay, and that's pretty simple, right? Which is 18 minus 30, which is negative 12 newtons. So it's 12 newtons that's counteracting the force of gravity. And that makes sense because we've been considering this downward force as a positive. So as long as you're aware of like sign conventions, it should all be fine. Let's see. 18 kilograms, 30, yeah. That's pretty much right. Yeah, I can't figure out a shortcut with this one. I remember there was one. I just don't remember it anymore. It's been a long time since I took AP Physics in high school, but you can keep on going. You see we're getting a little bit more complex here. So we have two blocks, right? 5 kilograms times 10 meters per second squared. So this is going to be force of gravity. Force of gravity, which is just going to be 3 kilograms times 10 meters per second squared. And you got tension force. So tension is going to be the exact same everywhere. Okay, so we can see that tension's going to be this way, right? The tension is still pretty much constant throughout the entire thing because the entire system is accelerating the same way. I think. I never actually thought about this, but I'm pretty sure it should work like that. You know what? If all else fails, we can learn that today by calculating the tensions in this string. Yes. So we're going to figure out these tensions and see. Let's see if the tensions are the same. I'm like 98% sure it is, though. But once again, we can go through the total forces. So now we need to be very careful with the signs on this one, right? Because this one is acting in complete opposite direction of this one. So when you increase this force, it starts going the other way. If you increase this force over here, this starts going the other way. So basically, these forces are going in opposite directions. They're counteracting each other. So if you have 5 kilograms on one side and 5 kilograms on the other side, they don't add together, they subtract, and it's at equilibrium. So you want to be very careful in this specific situation, right? And there's a couple ways you can be careful about like the direction. But personally, right now, I think this is a pretty simple like diagram to look at. Let's see. So I'm just gonna say, you can intuitively tell that this is gonna go this way, right? Just like intuition, this weighs more than that, and otherwise it'd be equilibrium. So this is gonna start falling this way. So let's say that 5 kilograms and 10 meters per second squared. So this is the total force over the entire thing. Minus 3 kilograms times 10 meters per second squared. Is equal to the total mass. So once again, we add all 3 of the masses together. Oh, I also forgot gravity and normal force, but I don't really care about that in this situation, if I'm completely honest, because it's irrelevant right now. So we got 10 kilograms, okay, is 5 plus 2 is 7 plus 3 is 10 times acceleration. Yeah? Stop me if this doesn't make any sense, okay? So this is going to be 50 newtons minus 20 newtons. It's going to be 30 newtons, okay? And 30 newtons is equal to 10 kilograms times acceleration, and acceleration, this is going to be acceleration is equal to 3 meters per second squared. Yeah? Okay. Well, I think I just remembered the shortcut. No, I'm just kidding, I don't remember it. Okay. So we now know the acceleration. Let's solve for the tensions, and let's see what is actually happening here. So let's do it on both sides. So let's do the left side. Ooh, there's not enough room left. Let me take all of this work and minimize it. So if you guys still want to see it, I'm not sure if you guys do, but it's up here somewhere now. Also, I see that there's a question. Could I do an FRQ? Let's see if that is still there. I'll be doing FRQ practices probably near the end of this semester. Honestly, I feel like the curriculum's really slow. In high school, I learned the entirety of Physics 1 in like one semester. And like, I feel like that's like a good pace for it. I feel like otherwise it's a little bit too slow. Because we've been on kinematics for a month. That's like a little too long, in my opinion. But we'll see what FRQ practices we have. So we have acceleration is equal to 3 meters per second. For our left side, right, so without the tension, zero tension is going to be 50 newtons, right? Because 5 kilograms times 10 meters per second squared is 50 newtons. But we subtract the tension from that, or you can add a tension, whatever it be, because like, as long as you're careful, it's fine. And it's just gonna like, it's just gonna change like a parts of negative, and like, tensions are pretty much like absolute value. You can't have a negative tension, but so 50 newton is gonna be 3 times 3 meters per second times 5 kilograms. The tension is going to be 35. You do the algebra, right? Let's do the right side. So the total force is going to be 3 times 10 kilograms, right? 3 times 10 meters per second, I mean. So 30 newtons plus tension is equal to, that's not right. Oh, no. I was looking at the other question. I was like, that turns out 0. But 3 meters per second squared times 3 kilograms. It's very interesting. Tensions don't appear to be the same. So T is equal to 19 newtons. If you look at the full force, let's see. Just as pretty much me just like seeing 16 newtons. So you have 35 newtons going in this direction and 19 newtons going in this direction. That means there's a total of 16 newtons acting on the entire, acting on this thing. 16 newtons times 2 times acceleration. That implies that this is accelerating at 8 meters per second squared. So I definitely did some sort of calculation wrong. Hold on. Newtons. Oh, this is 21, not 19. 21 newtons. I was scared for a moment. I was like, I just like broke the laws of physics. I was like, ooh. And this one is not 35. Is it 35? Yes, 35. Yeah, so this is 35 and this is 21. So that's 14. So 14 newtons is equal to 2 times acceleration, 7 meters per second squared. That's still not right. What did I do wrong here? Perhaps I calculated the initial acceleration wrong. 50, 30, 20. Oh, you see, I'm like really tired today. I'm like doing really, really basic math wrong. It's a total of 20 newtons, right? And the acceleration is going to be 2 meters per second. That's going to like throw all these calculations out the window. Yeah, I just switched these two numbers by accident. Sorry, I'm like really exhausted from a week of like homework. But yeah, if I did all the calculations correct, we can go back to this later, but I'll do all the calculations correctly in a moment. Okay, if you guys see me like do really basic math, like algebra wrong, make sure to call me out. Because like I'm just a human being and I'm not perfect. But yeah, that was a really simple thing to mess up. Okay, so let's go to this problem. I'm gonna go through this problem before I go back. And probably even like this problem, which is like, I guess the final level of complexity of this problem. Okay, let's see. So we have an inclined plane. If you guys know how to draw force diagrams, this one's a little bit more complex, and this is when we really need to care about our normal force now. Because our normal force is going at an angle. And you're like, whoa, that's so weird. Well, we'll see why we can do that in a moment. But we got normal force going up. Normal, force normal. And this is force gravity. This is force tension. Force tension. Fun fact about tension, right? You have a line. You have like two masses. Tension always points inwards. Always. So it always points away from the object. Whereas when you're like compressing something, this is something I learned in like another class. But when it's compressed, right, it always points out. Just fun facts about tension. But yeah, whenever you have a tension force, the arrows always point away from the object you're looking at, right? So we have force from gravity, force from normal force, and then you have tension over here, you have mass times gravity over here. You're wondering, but wait, this guy's on an incline. His force is not going to be like parallel with this guy, right? So what's going to be what's going to be force that's going to like act down on it, right? Because you can imagine, like, if this was a really heavy weight over here, this will start sliding down, right? Whereas when you have a different question, like this one, if this weight is super heavy, like let's say that this is like 1,000,000 kilograms. If this is just chilling here and you have like 0.01 grams on this side and there's zero friction, it's still gonna go down, right? But this one's not the same because you have some y force that is pointing downwards, right? So a little bit of force is pointing down. So we gotta consider that. Strong force diagram, because these force diagrams are very essential to understand. So you got inclined plane, got block. And this guy plus 60. And then you have gravity. So you want to find this force, right? So what I like to do, I like to point, I would like to draw an arrow down, right? I'm being a fool here. So you got normal force and you got this arrow pointing down, right? So this is going to be pretty much all proportional to all the forces, right? So you have this arrow pointing down, and if you look at like similar rectangles, right, it's going to end up that this angle is going to be 60 as well. So sine of 60 is equal to, so opposite, which is the force we're looking for, force in the y direction, over hypotenuse, which is mass times gravity. So let me go through that a little bit slower, right? Let me see if there was a way that my TA explained it in college that made a lot of sense, right? So when you're at sine of 0, right, the y force is going to be 0. So this is a weird trick to like do this really quickly, right? So let's say we have a flat platform, right? And you just have this guy here, right, pulling down. Yeah, this is a trick. I remember this. So 3 kilograms, 2 kilograms. And the only difference between this is that this has an incline of 60 degrees and this has an incline of 0 degrees. So it would usually be on a plane that's lifted up, but it's not. And this angle is 0 degrees over here, right? So that implies that the y force, there is 0 y force, right? If there is 0 y force, you know what else is interesting? Sine of 0 is also equal to 0. So that's just like a quick way of thinking about angles, right? So when you look at this problem, you see like, oh, there's 60 degrees, right? Should I use sine or cosine? Like, oh, so if it were completely flat, there would be no y force on this entire system. And that means I can just use sine because sine of 0 is going to be 0, right? That's just like a really fast way of doing this, but like you don't actually need to understand that. Like, it's okay if you like don't use that. You can just still use a traditional triangle method. At least like when I was doing physics, I had a lot of difficulty doing those triangles a lot, but yeah, you can just use the sine method. So that's going to imply that force in the y direction caused by this block is going to be mg times sine 60. The thing is, I do not know what the sine of 60 is because I forgot the unit circle. It looks like it's going to be 0.866. I think it's like square root of 3/2, yeah? And then mass times gravity, so it's going to be 3 times 9.8. It's 30 times 0.866. And 20, it's about 26. Hold on. Oh, this is in newtons. So this is in newtons, and this is just like the ratio of the force that's going to be in that direction. It's going to be 26 newtons. So let's go back to like the traditional way that we like to approach these things. So there's 26 newtons acting downwards. Okay. Yeah, I guess. Oh, now I look at this rectangle, not rectangle, triangle, and this probably, if you looked at the graph accurately, the diagram should probably be like more horizontal, or more vertical than horizontal. So this is going to be 60, this is going to be 30. That's why the picture looks a little bit off. But yeah, you can like, I didn't like intend for this initially because I probably intended this to be 30. But this block is actually sliding this way rather than going down. And you can see that inside the equation, right? So you have the total force is going to be 2 times 10, 2 kilograms times 10 meters per second squared. Minus what is going to be 26 newtons that we got from the other force is equal to the total mass. It's going to be 5 kilograms times acceleration. So this is going to be negative 6 divided by 5. It's going to be 1.2 meters per second squared. If you do the algebra correctly. Yeah. It's like my algebra skills aren't the most stellar today, but this guy is going down here 1.2 meters per second squared. And this guy is going up here at 1.2 meters per second squared. Now we can find the tension of the line. And it's going to be, because it's like one consistent string, it's going to be consistent throughout the entire thing. So we can just find the forces on this guy, right? So the tension force is going to be definitely a lot more than the force of gravity. So the force of gravity is going to be 20 newtons from 2 times 9.8, or 2 times 10 meters per second squared as a simplification. 20 newtons, so without any tension, minus tension force to mass. So it's going the opposite direction, right? So we need to be careful about the signs on this guy, right? So this was initially going down, and now it's going up, and now the acceleration is in the upwards direction, and we denote that with a positive number, or a negative number in this situation, negative 1.2. It's going to be 2. Yeah, this is going to be 2 times 1.2, just 2.4, equal to 20 minus t, and t is going to be about 17.6 newtons. About the approximation, right? Okay. Are there any questions? Just want to check back, see if everyone's alive. Everyone good? Okay, I'm gonna keep on going. Okay, this last one, I guess, is a mix of both the blocks, like at rest. So we've seen 3 blocks, right? We saw one block with like completely unhindered vertical motion, right? So it's just like a pulley and it's just dangling down, and there's 0 normal force. So we go from 0 normal force to, we have a second block that is on a slope, so there is normal force, but not complete normal force. So there is some sort of like y force acting on this. To a block that is completely at rest, it's just 2 kilograms just chilling there. And there is 100% unaltered normal force. So there is nothing that is like going to contribute to the total acceleration of the entire motion, like in terms of forces. Okay. So let's see. Okay. So we have this. Once again, we want to go back to our force diagram. We got this one going down, which is 30 newtons from force of gravity. We have force of tension, which we're trying to find. I guess you needed like solve for acceleration. Did we solve for acceleration? Oh, we also solved for tension. Yeah, we did complete that problem. Okay. So we got normal force. Let's draw normal force on this guy. Force of gravity on this guy. We got the force of tension, 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 and then these two forces cancel out. Force, normal force, and gravitational force. So let's calculate the total amount of forces that are in our system. So we start with 30 newtons, right? And we can, and if you think about like the same thing that we talked about earlier, when we talk about the shortcut that we did earlier, we found like the sine of 60, right? Let me just reiterate one more time just to make sure it makes sense. But let's see. So sine of 60. So if it were sine of 0, it'd be at 0, 4. So we want to be at sine of 60. So minus sine of 60. Multiply that by force of gravity, 2 kilograms times 9.8 meters per second squared. Right? Let's see. Yep, and then that is equal to the total mass. So this is this guy plus this guy plus this guy, 7 kilograms times acceleration. I'm not sure if I did that right. Yes. Okay. We want to calculate this out. Let's see what thing I really need to calculate is sine 60 times 2 kilograms time. So 20 times sine 60. Seventeen point 17.32, right? 30 newtons minus 17.32 newtons is equal to 7 kilograms times acceleration. 13, let's do a simplification, 13.7. So let's just say I round this down to 17 newtons because I like to simplify. And let's just call this 13 newtons, right? It's equal to 7 kilograms times acceleration. Acceleration is going to just be 13 newtons divided by 7 kilograms. And that is going to be about a little bit less than 2 meters per second squared. Right? So let's go back. This is like a gross estimation, just as a heads up. So you can probably find a more precise answer if you use like 9.8 per meters per second squared and didn't round off this like 0.32. But yeah, as a gross estimation, we can do 2 meters per second squared as the total acceleration. So total acceleration is 2 meters per second squared. And then we find the force of gravity on this guy. Let's find the tension. This guy over here. All right. Okay. So we have 30 newtons. 30 newtons is equal to minus 2. Okay, 30 newtons plus tension, or minus tension if you want to write signs, but it's I pretty much think it's relevant. 2 meters per second squared times the 3 kilograms. So this force, that force, 6 kilograms, 30 newtons, 6 newtons. Let's do algebra. 24 newtons. So this is going to have a 24 newtons upwards force. And that makes sense because this block is going down, right? So there's still that 6 newtons that exists, like 6 newtons of force within this block that is still going down, right? So tension is 24 newtons, right? So, that's interesting. I actually don't think that the tension is constant throughout the entire thing. That's interesting or not. Because if you look at this acceleration, so if the entire system does go at 2 meters per second squared, yeah, that's very interesting because like if these two counteract, yeah, that's because like the wire is broken in the middle and you add an additional force out here. So the tension across this wire is not going to be the same as the tension across this wire, if that makes any sense. And if all objects are accelerating at the same rate, of course you're not going to have the same amount of tension in the entire rope because you have 3 different masses going on through the same acceleration. So yes, the tension would not be the same in 3 object systems. That's something I learned today. But if you want to calculate the tension of this guy over here, this one's pretty simple because you can just do mass times acceleration of this guy. 2 kilograms times acceleration, just 2 meters per second squared, 2, 4 newtons. And that's pretty much it. Okay. Let's calculate this guy back here. Well, I don't even remember. I just remember there's like a total of 22 meters per second squared. Okay. Yeah, we're pretty much winding down. Regardless, I think that's pretty much it for me today. Yeah, anyone else have any questions, like general physics? Anything about physics, physics 1, mechanics? Okay. Anyway, I'm gonna head out. That's okay with you guys. Once again, come back next Thursday, do more physics practice because practice makes perfect in these types of questions. Just need to do straight practice, especially if you do physics C, Met, some lot of practice questions. Yeah, I'm gonna head out. Thank you guys for stopping by. Appreciate y'all. Guys have fun studying for whatever you guys need to study. Okay?